So section 2.9, molar mass. We were looking at atoms and how crazy small they are, and the masses of protons and neutrons, etc., are like 10 to the minus 27 kilograms, crazy, crazy small. We cannot weigh individual atoms, but we often need to know how many atoms are in a given mass of a sample. I'm just going to close the door. And the reason we need to know numbers of particles is because chemical processes happen between individual particles. Oxygen and hydrogen combine in a particular ratio to make water. Well, when we want to know the number of atoms in anything of an ordinary size, we count them by weighing. If you went to the hardware store because you were going to build a fence and you needed nails to build a fence around a big backyard, you would not go in there and expect them to count out 1,200 nails, right? Nobody wants to do that, right? So how do they figure out how many nails to give you? They weigh them. They have a big bin of nails. You don't want to grab them with your hand because that's going to hurt, but they have this claw thing, and you scoop up nails, and they weigh them. And so you can get a good estimate of counting by weighing the objects. When we're counting large numbers of objects, we often use some units that specify a number of things. A dozen objects is 12 objects. A dozen always means 12, whether you're talking about donuts or people or photocopies gotten from the library because people forgot to print stuff out. It's a dozen is 12, right? And there's another unit like that, which you may or may not be familiar with, gross. A gross is a dozen, which means 144. Can anybody think of another unit that's a counting unit like that? How about for paper? A ream. How many pieces of paper in a ream? 500. A ream means 500. So chemists have our own unit for counting. It's called the mole. And you can think of it as the chemist's dozen, except that it's a lot bigger than a dozen. It's this nice little unit, mole. It's not mole. It's not a little half-blind animal that burrows underground. It's just M-O-L-E. And it has an abbreviation, MOL. I don't know why, but it does. I think, personally, molecules should have an abbreviation, but it doesn't. But a mole is just a particular number of things. It's 6.02214 times 10 to the 23rd particles. And we usually just use 6.022 because that's 4 sig figs, and that's good enough for most things. So 1 mole is equal to this many particles. And this is called Avogadro's number because of the work that Avogadro did, which led to us being able to calculate this number. And so it's named in honor of him. So I just have to tell you a little personal story. My husband's a chemist. I'm a chemist. And chemists often celebrate Mole Day because 10 to the 23rd, that's October 23rd. So October 23rd is Mole Day, 10 to the 23rd. So Mole Day is kind of a fun day for chemists. You know, the mathematicians have Pi Day. The Star Wars people have May the 4th. May the 4th go with you, or be with you. So Mole Day. So our 4th son was born on October 23rd. And he weighed 10 pounds. And he was 23 and a half inches long. And that was just so incredibly cool. The only thing better is if he had been born at 6:02 a.m. or p.m., that would have just been icing on the cake. But yeah, that doesn't always work out that well. But anyway, he's our mole baby. We toyed with the idea of giving him the middle name Avogadro, but we refrained from that, so he's safe. But this is a very important number, and you need to memorize it. 6.022 times 10 to the 23rd. It can specify number of anything, marbles, grains of sand, anything. Just like dozens can work for donuts or sugar cubes or cars or anything. This number is so huge, it's really hard to get your mind around. I'm trying to remember some of the analogies. I think if you had a mole of marbles, just regular ones, not the shooter ones, the regular sized ones, I think it would cover the surface of the earth to a depth of about a mile, something crazy like that. And you just think about it, that many marbles, it's mind-boggling. Oh, here's one I know for sure. If you had a grain of sand, this is really more of a how small is an atom thing. If all of the atoms in a grain of sand were as large as the grain of sand, they would take up about the amount of space of Mount McKinley. That gives you an idea of how small atoms are. I need to write these things down because I keep forgetting, and they're really fun and cool. So the second thing we need to understand about the mole is how it gets its specific value. And this again relates to the whole carbon 12 and 12 grams thing. So mole is a unit that we made up because we made up all the units, right? An inch is made up too. We make them up to be convenient. A mole is defined as the number of carbon atoms in exactly 12 grams of carbon 12. Now, does that sound a little bit familiar to something we talked about on Tuesday? There was something about carbon 12, right? 1 AMU was equal to 1/12 the mass of one carbon 12 atom. And here we have the carbon 12 again, and 12 grams. There's a relationship between atomic mass units and moles and grams. When we convert between moles and number of atoms, it's just like converting between dozens of eggs and number of eggs. It's just that we're not using the number 12, we're using this really weird number. We're just using scientific notation, and we get our conversion factors from this. It can be 1 mole per 6.022 times 10 to the 23rd atoms, or we can upside down it. We can invert it. But please do not tell me that 1 atom equals 12 moles. That's like saying 1 egg equals 12 dozen eggs. It doesn't make any sense, right? So let's use this in an example calculation. Gallium is a key element in solar panels, calculators, other light-sensitive electronic devices. Very nice, completely unnecessary. How many gallium atoms are in 2.85 times 10 to the minus third moles of gallium? Well, there's a number in there. Let's write it down. 2.85 times 10 to the minus third moles. And how many atoms? So we're given moles, we're trying to find atoms. Mole is like a dozen. A dozen is a particular number of objects. A mole is a particular number of objects. And so we're going to have atoms on top and moles on the bottom. Because we have this relationship that 1 mole equals Avogadro's number of anything. Here we're talking about atoms. So we've got a mole, we want to know how many atoms. We're going to say 1 mole is 6.022 times 10 to the 23rd atoms. Now, you have to use scientific notation on your calculator when you do this, because I haven't seen a calculator yet that has 24 digits. I really need to get a calculator I can open with one hand. Or I could just remember to take it out. That would be nice. So remember to use the EE or EXP button on your calculator. Don't do times 10 or use the 10x button. 2.85 EE 3 minus or minus 3 times 6.022 EE 23 equals And I get, I'm going to round this to 3 sig figs, 1.72 times 10 to the 21 atoms. Any questions? Everybody's had chemistry before, but it might have been a while. This is just a new conversion factor. We're using the same dimensional analysis technique, just putting the units in so they do what we want them to do, and then the units tell us where to put the numbers. We don't have to think about, oh, am I supposed to multiply by Avogadro's number or divide? The units just tell us what to do. Any questions? Is your calculator giving you the right number? If your number, if this coefficient part of your scientific notation is correct, but the exponent is wrong, it means you're communicating incorrectly with your calculator with the EE button. No questions. Okay, that's fine. So here's another example. At rest, a person inhales 9.72 times 10 to the 21st nitrogen molecules in an average breath of air. How many moles of nitrogen atoms are inhaled? And you may be thinking, why would I care about this? Because it's on the PowerPoint, we have to care about it. So there's a number. Always a good idea to write the numbers down. Always include your units. Nitrogen molecules. So this is molecules. Those are particles. See, wouldn't it be nice if that had an abbreviation? That's a really long word. How many moles? This is the question. How many moles? I want to multiply by moles and divide by molecules. MOL looks like it should be the abbreviation for molecules, and I personally think it should be, but it is not. They are very, very different. How many molecules in 1 mole? Avogadro's number, 6.022 times 10 to the 23rd. Molecules cancel molecules. I'm left with moles, the unit I want. So I've got 9.72 EE21 divided by 6.022 EE23 equals. And this is telling me that is 0.0161 moles. Any questions? Is your calculator giving you the right answer? I am the calculator whisperer. If your calculator's acting up, I can speak to it for you. It's its fault. It's not your fault. Calculators are squirrely. Conversions with Avogadro's number are important in chemistry. So knowing the relationship between moles and number of atoms doesn't solve our problem of being able to count atoms by weighing them. We still need another conversion factor. We need to know the mass of a mole of atoms. The mass of a mole of atoms is called the molar mass. Molar mass is the mass of a mole. Atomic mass is the mass of an atom. So this guy right here is important. That's probably why he's in blue. I'll point to him. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. And this is because we chose the units to work out this way. It's not magic. But we learned that on the periodic table, the mass of an atom, the average mass of an atom of, say, copper is 63.546 atomic mass units. 1 mole of that is 63.546 grams. So the numbers on the periodic table do double duty. They are the mass in grams of 1 mole or the mass in atomic mass units of 1 atom. Aluminum has a mass of 26.98, a molar mass. That means 26.98 grams of aluminum is equal to 1 mole of aluminum atoms, which is Avogadro's number of aluminum atoms. A mole of carbon is also Avogadro's number. A mole of helium is also Avogadro's number of atoms. But a mole of helium weighs a lot less than a mole of aluminum because helium atoms are a lot smaller. So the lighter the atom, the less mass in 1 mole of atoms. So a mole of helium is only 4 grams. A mole of carbon is 12 grams. A mole of aluminum is 26.98. These make really nice conversion factors. So that molar mass, and this is super, super important. The molar mass in grams per mole is what we're going to use to convert between grams and moles. So we take 12.0 grams of carbon is equal to 1 mole, and we can make 2 conversion factors out of that. 12.01 grams per mole or 1 mole per 12.01 grams. So let's use that in a problem. Silver is used in jewelry and tableware, no longer in U.S. coins. Then the coins are more value than their face value. That doesn't work out real well. How many grams of silver are in 0.0342 moles of silver? That whole first sentence was just fluff. .0342 moles of silver. And they're asking for grams. So we want to multiply by grams of silver and divide by moles of silver. The relationship between moles of an element and its mass in grams is on the periodic table. So silver has a molar mass of 107.868 grams. 107.868. They say there's 3 symptoms that you're getting older. The first one is that your memory goes, and I can't remember what the other 2 are. The moles cancel out. And so we're going to take 0.0342 times 107.868 equals. How many significant figures should I report in my answer? 3. Because the number I'm starting with has 3. So 3.69, and the unit is grams of silver. Now, is this molar mass an exact number? No. We talked on Tuesday about how it's calculated. It's calculated based on percent abundances of the different isotopes and on the masses of each of those isotopes. Those involve measurements, and so there is uncertainty. This periodic table has a varying number of significant figures for the different masses. Some periodic tables round them all to 4 significant figures just to be convenient. So whatever periodic table you're using, just use the number of significant figures that are in there. Usually the number that's given in the problem is going to limit the number of significant figures. But you definitely don't want to round your molar masses. You don't want to say, oh, well, that's about 108. Not if you're doing a real calculation. You want to use the best number you have. Any questions? Avogadro's number is not exact either. Yeah, a more exact version of it is 6.02214 times 10 to the 23rd. A lot of times we just use four digits, 6.022 times 10 to the 23rd. But if you're doing some very precise work, that could limit your sig figs in your answer. Any other questions? Graphite is the crystalline form of carbon used in lead pencils. How many moles of carbon are in 315 milligrams of graphite? Well, we have one number in here, 315 milligrams. And they want to know how many moles. Can we go directly from milligrams to moles? No, because grams and moles are the relationship we get from the periodic table. So what we need to do is we need to convert milligrams to grams, and then we can convert grams to moles. So this one's a little bit more involved. 315 milligrams. So first we need a factor relating grams and milligrams, and then we need another one relating moles and grams. Milligrams to grams to moles. Milligrams to grams to moles. Dimensional analysis. We want milligrams in the bottom, so these guys are canceling out. We want gram in the bottom, so these guys cancel out. And then we stick units in there. No, those are the units. We stick numbers in there. So, yeah, just any old number, just some random numbers. No, we don't want to do that. Here's a prefix, milli. What does milli mean? What does it stand for? 10 to the negative 3. So I'm going to put 10 to the negative 3 on the other side of the line. I don't want to put them together. Okay? Now, if you're doing, oh, well, but 1 gram is 1,000 milligrams. That's fine. People get confused, though, and they do the equivalent of saying that a foot is 5,280 miles. That's what happens when you put the number on the wrong side. You get ridiculousness and incorrect answers and poor grades. So we don't want to go there. So if you follow this pattern, you'll never get them backwards, and you don't have to think about it too much. You put the prefix on one side, and you put its mathematical meaning on the other. They're all powers of 10. Then over here, grams and moles, that's the molar mass. Molar mass, mass of a mole. 1 mole, and we look on the periodic table for carbon, and this is 12.011. 12.011 grams. Don't switch those numbers either. That won't work. Then we do the math. 315 times 10 to the minus third. There's a variety of ways you can enter that. I think the most straightforward for easily confused students is to think of that as scientific notation. So we've got 315 times 1 EE minus 3 divided by 12.011 equals. My initial value here had 3 sig figs. Grams to milligrams is exact. This is not exact, but it has 5. So my answer is going to have 3 sig figs and be 0.0262 moles. Any questions? These are very important types of calculations. So we can count atoms by weighing in this manner. We've got the mass. We can convert the mass to the amount in moles using the molar mass, and then we can convert that to the number of atoms using Avogadro's number. So grams to moles to number of atoms. That's the kind of long, drawn-out method. It works. It definitely works. Another example. Iron is the main component of steel and thus the most important metal in industrial society. It is also essential to the body. Fluff. How many iron atoms in 95.8 grams of iron? There's the question. So we have 95.8 grams of iron, and we need to find number of atoms. So let's think about it this way. What's the molar mass of iron? 55.847. So 55.847, we're just getting that off the periodic table, grams of iron equals 1 mole of iron. How many atoms are in 1 mole of iron? 6.022 times 10 to the 23rd. You'll have that number memorized by the end of the day, whether you want to or not. So on the previous slide, they were saying we should go from grams to moles to atoms. But doesn't this give us the relationship between atoms and grams directly? If this equals a mole and that equals this, then this must equal the first thing. I think that's easier. So I'm just going to write that up here. So I've got grams, I want atoms, and I need grams in the bottom. 55.847 grams of iron is equal to Avogadro's number of atoms. The grams cancel out. (95.8) times 6.022 BE23 divided by 55.847 equals 1.03 times 10 to the 24th atoms. Is that a reasonable number? Pardon me? In 95 grams, is that an amount of iron that we can see? Is it big enough to see, to hold in your hand? Yeah, it is. So that's a macroscopic amount of iron. Would we expect there to be a lot of atoms in there? Yeah. Anything that you can see is going to have a lot of atoms in it. And so we expect to get a really big number. If you're ever calculating number of atoms and you end up with less than 1 atom, is that possible? No. So if you get, 1.03 times 10 to the minus 4th atoms, something went wrong. Any questions? Well, here's another one. Manganese is a transition element essential for the growth of bones. More fluff. What's the mass in grams of 3.22 times 10 to the 20th manganese atoms, which is the number found in 1 kilogram of bone? This question has 2 numbers in it. Do we need both of them? Might not be obvious. Well, let's write them down and see what happens. Because this is part of decoding the word problems. So 3.22 times 10 to the 20th manganese atoms, and that's the number found in 1 kilogram of bone. So I wrote the numbers down with their units. What am I trying to find? The mass in grams. Well, can I convert number of atoms to grams? Sure, I just converted grams to number of atoms. For manganese, we get that relationship from the periodic table, like for everything else, 54.9380. 54.9380. That's the number under the syllabid symbol. Element symbol. It's the symbolant. I don't know where that came from. The talking machine is malfunctioning. 54.9380, the number under Mn in the periodic table, that means the mass in grams of 1 mole of manganese atoms. 1 mole of manganese atoms is Avogadro's number. Atoms. There we have the relationship between grams and atoms. So we can do this in one step. We want atoms on the bottom. We want grams on top. We're careful not to swap units and numbers. They have to stay together. This 54.9380. Atoms cancel atoms. 3.22 EE20 times 54.9380 divided by 6.022 EE23 equals 0.0294 grams. Did I need 1 kilogram of bone? No, I didn't. Sometimes there's extra numbers in a problem. Look at them, but you don't necessarily have to use all of them. Is this a reasonable mass for the amount of manganese in 1 kilogram of bone? The train thinks so. What if we ended up with 29 kilograms? Would that be reasonable? Could you have 29 grams of anything, 29 kilograms of anything in 1 kilogram? No. The thing that the part has to be less than the mass of the whole thing. This is less than 1 kilogram, so as far as we can tell, it's reasonable. It's definitely not ridiculous. When I say reasonable, I just mean not ridiculous, not impossible. Any questions? You're really low on questions today. End of chapter 2.